Hello and welcome to this video about matrix proofs. In this video we'll prove this theorem about the identity matrix. That is, that multiplying it by any matrix on either side will leave the matrix unchanged. So this is the matrix equivalent of 1. A can have any dimensions, and the identity matrix must have the correct dimensions to multiply it by A, and this can change depending on which side it multiplies A on. The identity matrix behaves like the number 1. But it isn't called the 1 matrix, probably because it mostly has 0 entries in it. This is what A is equal to in ijth entry notation. And this is what the identity matrix is in this notation. We're using a special function called delta. And this is how delta is defined. It's equal to 1 if I and j are equal, otherwise it's equal to 0. So this is what matrix A looks like in terms of all its entries. I've represented a square matrix here, although this proof can work for any shape of matrix. And this is what the identity matrix is. It has a diagonal of all 1s, with all other entries equal to 0. This is the behaviour of the delta function. So now to prove this theorem. We'll start with the left-hand side and write it in ijth entry notation. Then we'll use the definition of matrix multiplication to get this product, bringing the two expressions in square brackets into one pair of square brackets. I'll write this entry out in dot notation to follow it more closely. So all of these delta functions will be set to 0, except for one of them, which is set to 1, according to the definition of the delta function. And so all of these terms will simplify to be this. And all of these zeros can be eliminated, being the property of 0. Which gives us the matrix A when we use the variable name to get this result. So we've partly proven this theorem. So now to prove that multiplying A by I on the right gives us A. It's similar to the last calculation, but different enough to need its own proof. So we'll write this product AI in entry notation. Then we'll bring the entries together into one square bracket using the definition of multiplication. Then we'll expand it out into dot notation to have a more careful look at this sum of terms. Then we'll evaluate all of the delta functions. They'll turn into either 0 or 1, mostly zeros though. This time they'll multiply by the entries of A on the right. Then we'll simplify this sum of terms. We'll eliminate the zeros. And then finally we'll write this matrix out using its variable name, thereby completing the proof. So we've proven this theorem. So now I'd like to try proving this theorem differently. We'll write out the identity matrix like this, as an identity matrix that can be of any size. We can write it out as separate column vectors like this. So these column vectors are standard basis vectors, and we can write it out like this as a collection of standard basis vectors. We can collect the rows together like this. So then we can write the identity matrix like this as a collection of standard basis row vectors. And we can write out the matrix A as a collection of row and column vectors where R stands for row and C stands for column. So we'll calculate the dot product for these two vectors because they'll be multiplied in the matrix later. We'll expand them out so as to look like column vectors. These two rows line up so that the ith element of this standard basis vector is 1. While all the other elements are 0. And so using the dot product like this picks out the ith element in the column vector. So now to perform this dot product on a column vector as we'd find it in a matrix. These are the entries of the column in the matrix. And so this dot product picks out this element in this matrix. So now to prove this theorem again using this line vector notation. We'll prove it for IA. We'll rewrite it in line vector notation. Multiplying these matrices together gives us this array of dot products, which will give us a matrix with these entries. And this so happens to be the matrix A. Now to show it's true for AI this time, we'll get these matrices in line vector notation. Then we'll get this matrix of dot products, which will give us a matrix with these entries, which will give us the matrix A. So that's it. We've proven this theorem another time using a different matrix representation. So I hope that you've found this video to be helpful and educational, and even interesting. Please click like and subscribe if you did. Feel free to post anything helpful in the comments and to share this video. and thanks a lot for watching.